Um, so, it's, oh, thank you. Okay. It's actually a great honor for me to be here to present our work. My sincere thanks go to Vimeo and Mozilla. And this is actually the first time we present our work in front of the highly respected people right now sitting in the audience doing compression. So I'm talking to the compression communities. There's no joke. So basically, there's several messages I'm going to pass out. But before that, because there's going to be a lot of updates after my talk. So there's a few more exciting talks after mine. But there's the first message that I want to talk a little bit about the use of machine learning to video compression. Actually, I was very against machine learning to be deployed in the field of video compression at maybe 2 years ago. To me, compression is a mathematical problem, so we tackle it with using signal processing mathematical problems. And on the other hand, in contrary, machine learning is like they tackle a problem more like a black box. You have the input and magically have some outputs. So even, because I'm from our startup, and when we go to the investor, they seem very highly put a lot of bet on the use of machine learning. They said, oh, you are doing encoder for your business. What if someday, and someone invented a huge neural network, and then whatever input is for the video, the neural network will compress it and then transmit it into the decoder. They use some other neural networks to reconstruct the video. Now, what will be the use of your video encoder? I don't have an accurate answer to that, but my answer right now I can tell is for the next 3 years, I would say the video compression will still more or less stay in the current shape. But one message I want to pass it out is we can't deny the leverage of machine learning in the field of video compression. That's something I want to talk a little bit here in the first message I want to pass out. So what could be the use of machine learning into AV1? I don't have to put a lot of effort in this because everybody knowing about AV1, and then there's 42 members right now, even the most recent one who joined the community of Alliance for Open Media is Samsung. And then AV1 has definitely a great potential, showing a great compression efficiency. So the red figure has shown that this report from the MSU, and they just released it, but the result actually from last year. But again, they show that compared to 2004 and 2005 AV1, not only a royalty-free codec standard, but also it has a great potential in terms of coding efficiency. So we want to pass the message to everyone. I'm also very happy to see there's a few familiar faces sitting in the audience that we once worked closely together for the finalization of AV1. I'm definitely a great lover and believer of AV1. So whether AV1 can leverage the use of machine learning, I would say at least in the overall, the two-dimensional motion estimation plus the motion estimation plus the two-dimensional transform, for this kind of architecture, machine learning can still have several aspects that it might tackle or help out on the optimization of the encoder design of AV1. So there's 4 aspects that I list here on the left side of this slide. The first one is you may think of the use of machine learning to help improve the coding efficiency when you design an encoder. For example, to use machine learning to do a little bit improvement for the design of rate control. There's one example I listed in the right-hand side of this slide. So LibOM, everybody knows that it's kind of like a benchmark code base for AV1 encoder and decoder. I list throughout the video AV1 standardization. LibOM was sitting there and it implemented all the tools. So when you talk about AV1, you can't just leave AV1 out. Inside AV1, if you look at the CLs, the code, there was a big improvement. Previously, the gulp structure is around 12 majority. Then it moved to the use of a hierarchical structure. So there's a gulp size of 16, and there's several layers there. So when you design this structure, you can't get away from how you design a good rate controller. So there's several parameters you have to optimize. For example, the keyframe booster and the out-ref booster. So how many bits you allocate supposed to those keyframes, and how many bits you allocate to the frames across different layers. There's quite a parameter down there. So actually, inside the libOM, the current parameters are coming from a method of machine learning. So it's basically leverage the use of a tool referred to as Google Vizier. And it's not publicly available, but it is the driver behind a cloud-based solution down there. Because of the use of machine learning, sometimes I think we design the parameters of encoder from empirical. But when you tune one parameter, you have to think, oh, there's another parameter that you have to worry about. Rate controller sometimes is very hard to tune. But I have to say that by use of Google Vizier to design and finalize those figures in the libOM, it does help to improve the coding efficiency of libOM in that tool by about 30 to 35% in terms of BD rate using the PNCR as a metric. So that's one thing that you can use machine learning. And second thing is you can speed up the encoder through the use of machine learning. Now we give you more results and examples down there. There's two more things that you can leverage machine learning. The use of machine learning in the pre-processing. I think Mark from YouTube has just mentioned that when you give those UGC tons of videos, they have artifacts, blocking artifacts, they have a lot of noises. And at those times, you want to use machine learning to think up what kind of noise or what kind of video quality you try to restore or recover. For example, this technology was not widely used in the Western country, but it's widely used in China, like Eastern. People are trying to beautify the faces, and they like to see those beautiful faces. Right now, it's a must-do feature in the live streaming. And when you do the beautify faces, you basically remove, like my face, we have dots and wrinkles. And you remove that, by removing that, you remove the high frequency signals from the video. Actually, you do a lot of denoising, but you make your video not only beautiful, but also more amenable to the compression. So which area, what kind of information you're trying to remove, machine learning can also kick out to help you that. To have a pre-processing module may help to you compress the video better and with a better quality in terms of subjective justification. And the first thing is everybody talking right now about super resolution. So I think the conference of CVPR who just passed, they have the great success that so many people gathered there. So you like the topic. There's a topic called super resolution. There's so many contributed papers. And super resolution, without a doubt, can definitely also help compression. If we do, for example, live streaming and the bandwidth is very limited, but the end device may have a lot more power, then you can stream the videos using lower resolution. For example, you want to do 720p, you can only do 480p or even 360p. On the other hand of the devices, when you do the playback, if you use super resolution, you can bring up the resolution back to 720p or create an even higher resolution, say 1080p. So this is 4 things you might be able to think of, whether to leverage them to the compression. So I'm not saying that you have to leverage those techniques, but machine learning is actually will be there in one way or the other to affect our compression community. So this is some talk that I just mentioned. How do we use machine learning to speed up the encoder? So there's several examples also sitting in the code base of libOM. For example, great complexity of AV1 coming from the partitions. And in VP9, there's only 4 partitions sitting there. So we are talking about non-partition, horizontal, vertical, and split. 6 more partitions mode have been added to the AV1 standards. And for every partition, you have to go through all those kind of transform and mode selection. There's one work actually that has been contributed for the speed up for the HEVC encoder. So I listed a paper down there. It is research work, but the speed from this research actually does inspire some of the idea that we implemented already in the LibOM for speed up, especially for the how do we pruning the partition mode at a certain stage. When you can avoid the, there's 2 partitions that maybe you can try to avoid in one layer, then a lot of encoders complexity that you can end up with reducing. That will help a lot. Another part is, at least down here, what kind of machine learning actually we can use for speed up the encoder? Because when we talk about machine learning, a lot of people talk about deep learning, talk about maybe 128 layers, with a lot of layers, a lot of modes, and tens of thousand parameters. Those definitely will add more complexity to the encoder. But when you talk about the speed up, you don't have to use those deep learning neural networks. In LibOM, there's several parts that we leverage the use of machine learning, for example, speed up and truncate which transforms or transform type or transform size. So there's 16 transform types, as everybody knows, in the AV1 standards. There's 4 types for each direction, and then for considering horizontal and vertical, there's 16 modes altogether. So you can train a small, simple neural network to help you select which type of transform you're supposed to use for a specific block. And those neural networks can be very simple. For example, you can just adopt 1 or 2 layers, and each layer may only end up with 128 nodes. So altogether, you don't have that many parameters. But also, when you do the mode decision, it's a learning process. So when you try to do the encoding, you actually can learn through the encoding of your process. For example, you try to encode a 1080p frame, then when you already get to in the middle, you already have a lot of blocks. Those modes can help you to train and help you neural network learn which specific, for example, you can extract like the variance, medians with some features very easily to be attained from a block first. Now you input those features into the neural network you already trained, you already learned from the existing block that you already encoded. Then that will give you a good indicator what kind of mode you maybe end up with, or what kind of stage you can terminate earlier. So I think there's a lot of empirical parameters or hard-coded parameters that we put into the encoder. So whenever you see that parameter exists, theoretically, you can replace those existing schemes with a neural network or machine learning type of approach. Okay. I won't talk about that much, but basically there's another work. This is for post-processing. So this work also from a research paper. The idea of this is when you look at coded video, you have I frame and P frames. A lot of time you end up with good quality for I frames, but for P frames it's not so good quality. And you can also use sort of machine learning type approach to bring back the good quality of those P frames and borrowing the information from those I frames. That's the key idea of this work. I'll skip this slide. And there's another work. This is last work that I'm talking about the machine learning based. We implemented back in with a collaborated project between Google and Purdue. The idea of this is still, we talk about a lot about video synthesis and analysis. So the idea, I think this idea has been sitting there for a long while. You can analyze the content of a video. You try to remove those content that can be synthesized. I decode it, end up with a better or larger comparison ratio. And this work is trying to actually leverage the use of global motion vectors that is standardized within AV1. And the use of this is try to find certain areas that can use those global motion to recover. That's an essential idea. But when we talk about the video compression, I think this approach, the synthesis analysis, when you apply this approach to image codec, you end up very good result a lot of times. But the thing is, when you apply that to video, the biggest problem of this approach is the consistency across frames for a video. Maybe sometimes you have a good result in one image, but when you play back, you can see some area that you use synthesis that oscillating down there. It's very disturbing. So for this approach, we had our first try. We only try to synthesize those frames that end up in lowest layer or highest layer inside a hierarchical layer, basically for those PB frames. And we use machine learning to identify which area may be better to use such kind of scheme for analysis and synthesis by the global motion. That's where the machine learning part kick in. And it's still a research result, but the first time we see a good result and a better comparison ratio using such kind of scheme. That's the first message I pass out. And second one is here I try to introduce some of the results for our stuff we have achieved in the field of AV1 encoder optimization. Before that, I gave a brief overview of the current AV1 encoder and decoders development. A lot of talk today will cover this, but still for the completeness of my talk, I will still review the current status of the encoder and decoder of AV1. For the decoder part, and I honestly think I actually do not have to talk about it because everyone said we just use David. And this is the fact that because the existence of David, and at least for the software optimization of AV1 decoder, I think pretty much everybody think, okay, our work is pretty much done. We just rely on the evolving and development of David. That's the case also to ours. We are very impressed by David. David has a great advantage to us. So I list some of the advantages down here. This slide was borrowed from Nathan. So I put his name down, and I pass out this message slide. And so David, I think the goals of David is also the advantage of David. It is a smaller binary size, it's low CPU utilization, and it's multi-threading wise, it has a super performance, and it has been optimized for cross-platforms. And I heard from Runner that, so at least down there for the right side, I added one item that ARM optimization of all the kinds of different transforms. As I said, there's 16 transforms, there's many transform sizes. Those optimization code will be loaded to David soon, because it's open source. Therefore, David has been widely leveraged by, I think, I delete that page because I know Runner will talk more about it. So David has already been incorporated within Chrome. And if you wanted to ever think of using a A1 decoder playback on the mobile devices, then you can rely on David as well. So here I mainly listed that the mobile device performance for David. Here is also borrowed this slide from Nathan. It shows that performance, how David performs in all kinds of different iOS devices. So I believe the rightmost devices is the most recent iPad Pro. So from this figure, as claimed by Nathan, that AV1 actually is ready to be playback for a 4K resolution in the iOS device. So that's a message we want to pass out to the rest of the world, that AV1 is ready. AV1 can be leveraged or for any use cases for potentially on the mobile devices. Because we are a startup, we are mainly customer-driven. Even we develop so-called long-term product, we still want to make sure that we will end up with some short-term users who really want to deploy our products. So when we get this message to our customers, say, wow, AV1 is really there. I think after today's message, when Thomas and Sheldon, the Cisco, send out the message that AV1 can do real-time 720p or 1080p 30 frames, RTC kind of usage, I think everybody got the message, wow, AV1 is really coming. We really need to start seriously consider use of that or incorporate that into our products. And the last figure, I just want to say, yes, I still have this slide. I remember that all the browsers and then already incorporate David. But this, I think this kind of slide is still kind of old. It should be around, I think, March of this year. There should be a lot more progress that have been made by David. And the last, in this session, that I have a review down here about the AV1 Encoder. So everybody knows that there are 3 public available AV1 encoder currently in the community. It's a LibOM, SVT AV1, and Ravi. And the right-hand figure, because many people say how this encoder performs, I have to say that we did our evaluation. But when if we put out our evaluation down there, I don't think it's fair because the evaluation for video encoder, it can be really biased. It all depends on which, I think the first part is which test set you're going to use. For different video sequences, our encoder can vary a lot. So that's why we didn't put our result. We put the result just we grab from someone who put their result in Twitter, but this result was back to February 2019. So I put a little figure down there because I did a screenshot of Hassan who just presented SVT AV1 to make sure that SVT AV1, Ravi, those are the 2 encoders, to me, are still under fast evolving and in their progress. There's still some tools that they have not developed. So it's not that quite fair if we compare them with some other encoders. To us, we don't want to compete at this stage between different AV1 encoders. So basically, we want to compare our result against 264 encoders and 265 encoders. That's also the message that we try to pass out to our customer. Please consider AV1. It shows so much progress advantage compared to APVC and H264. So consider to use that in that aspect. So the third session is start to talk to our own encoder. We call it Aurora. And our encoder, we have mainly, I think typically there's 2 scenarios. One's a video on demand. The other is the RTC use case. So for video demand, we have reported the results down here in 2 aspects. The first aspect is we compare Aurora against X264 and X265, mainly using their very slow speed level. X264 and X265, the setup we list here for the command line, and we also list here the configuration of our hardware. And the result is, in this table, we chose the test set of a JVT VC test sequence. And the reason we use that because that test sequence has been widely used. It's better for that standardization of HEVC, so we just use their test set to do the comparison. We chose the most, I think, relatively popular metric, once PSNR dialysis remap. So the current status of our encoder is compared against X265 very slow. Our AV1 encoder is about more than 30% faster compared to X265, very slow, and around 20 or a little bit more percent in terms of BD rate, both using PSR or minmap compared to against X265, very slow. Compared to X264, very slow in this data set, is actually definitely we can achieve more gains for the bit rate that we have chosen. So it's about more than 40% bit rate saving compared against x64 very slow, but we are not as fast for our VoD use case preset. This is more details about the comparison result. So left figure is for the PSNR-based result, and the right one is VMAF because JVT-VC has about 4 resolutions from 480p all the way to 2K. And the next one is we report the real-time encoding results. So before I came to this event, we were thinking we're doing good for our real-time cases because we implement the incorporation of our AV1 encoder, our Aurora encoder into FMPEG, and also incorporate within w.r.t, actually following the same RTC draft. And like I said, we are mainly customer-driven, so our customer passes the message that, oh, we know AV1 is slow, so you don't have to go up to that resolution. So what we have been mainly focused on is, oops, I think I messed up the slide. I have to come to this slide first. So we mainly focus on 480p, 15 frames per second, and 30 frames per second up to. So we provide to our customer with 2 presets of speed. So Aurora has a 1 pass fast and 1 pass faster. So we list the comparison result against the x64 very slow. So in this case, we show that we can do 480p for 2 different. For the faster, we can encode 1 pass 480p for about 45 frames per second. But I have to say that this result, because we are trying to serve our customers, so this result coming from the beginning of May, we make progress. And then yesterday, I learned that Cisco will present the result of 720p, 1080p, and I talked to our team, please upload the newest results so that I can present. So next slide is going to, let me see. Next slide, this slide is showing that our most recent up to yesterday's result for our 1 pass AV1 encoder Aurora. So you can see that from here, because it's really we got a big help from Mozilla. We also established our own AWCY, our compressor system, and we have a chunk of videos we usually use. You will be able to see that. So what kind of video we have chose to do our test. And for this one, we want to see that yesterday's version compared to the version that I just presented in the previous slide, we achieved in 2 aspects. BD rate, we are now 7% better in terms of PSR. We actually, in our BD rate, we not only, because AWS not only PSNR, it's also SCM, it's PSNY, all kinds of data. And speed-wise, right now, yesterday's version compared to the slide in the previously, we are about 44% faster. So 7% in terms of BD rate improvement and 44%. From today, we're starting to look at 720p and 1080p real-time communications. Thanks a lot for Cisco's result. But one thing we want to see is our rate control. We're able to say that we have a good rate controller, and we compare our rate control in a very granularity level. And so for we just randomly chose 10 sequences that we monitor the rate control compared against the x64 rate control. I think x64 rate control has been, at least to the best of knowledge, has been widely acknowledged as a good rate controller for the real-time uses. So from our sake, except one sequence here, we show that in the higher bit rate, our encoder bit rate has output too low, maybe because that content is just so simple. It's not worth to have a high bit rate to encode that particular clip. But for all the other sequence that we chosen, our rate controller do show that a great fidelity to the target bit rate that we set up. So I missed out one part, so I have to go. This is actually for the VoD cases. And we have step 1 step further, that we have the Aurora AV1 encoder plus the content adaptive encoder. So the CE down here, I have to say that we do have some machine learning part that we have incorporated. The goal here is still customer-driven, because when the customer look at our video, they don't care about VMAF or PSR, whatever metrics you want to create them. All they care about is the subject quality. So even though they would say, please give me the figures that you show that you do have the BD rate improvement for whatever metric, but finally they will justify our encoder using their subjective evaluation. So for this work, we particularly design for our customer. We particularly show that there is a potential. I don't want to compare this with the existing AV1 encoder. Again, I want to pass out the message that if you incorporate certain machine learning or subjective evaluation or justification into your compression or encoder design framework, you might end up with a lot of great potential. So for this one, our scheme, we basically compared against the lowest encoder. One is the AV1 CPU 0. The other is the X265. I think it's, yes, X265 Placebo, the lowest speed. Forget about the speed level, but let's look at the bit rate that we save. For using VMAF as the objective metric, for our Aurora encoder plus the CAE mechanism that you incorporate compared against the LibOM CPU 0, we achieve a bit rate saving of more than 30%. Compared to X265 Placebo, we achieve a bit rate saving using VMAF for more than 40%. So this is a figure, the bit rate figure that we use VMAF. Okay. So that's all. And the last session, I want to say that what will be the next step for the standardization? There's a lot of techniques that people talk about. Again, I want to present a little bit more work regarding the use of machine learning for the next standard. I know there's a lot of activities using machine learning and proposed to VVC. It seems to end up with no kind of neural network proposal has been adopted by VVC. But again, when we talk about AV2, there's a lot of potentials that we can bring the new tools to this new standard. I still hope that AV2 will be open. It doesn't mean neural network machine learning will win, but there is a potential showing there that it actually increased the ceiling that we once set up for the video compression capacity. So two things. One is, again, for the use of machine learning for in-loop filtering. This is a clinical work we have done with a professor in China. And this work is basically extending the work of in-loop filtering, or in some sense, extending the work of the restoring filter or the CDF or some other tools that has been already incorporated into AV1. So this work has shown an advantage of more than 0.2 dB compared to the in-loop filtering already adopted in AV1. And another one is the same thing for the post-processing. Previously, I mentioned the work to use the post-processing to increase the quality of those not so good quality and borrow the information from the iframe. So this is another work that has been conducted to use machine learning and do a multi-frame enhancement as a post-processing stage. So those could be a part of the future network standard, or it could be some direction we might be able to pay attention. We might be needed to pay attention for our next step of work. So that closes my talk. And the last slide is because we are a startup, so I just want to say that why we could do the work that we are doing. We are a team, definitely still, and myself, I was one of the engineers for the standardization of AV1. Our team, we are dedicated video encoders. We actually are very passionate about the video encoder, as many of you, or all of you, right now sitting in this room. And so we show that our team used to be from those encoders optimization. If you pay attention to the MSU result, there is a KSC 265, and the engineers behind that encoder right now in our team. And also for the standardization of AV1, our team contributed more than 200 CLs to LibOM. I show some figures down here, especially it's my honor to, with Oliver and Jai, we met in the NAB, and I really appreciate Google. They show our demo of AV1 in the Google Cloud booth, which attract a lot of traffic and help us to do the PR. And on the bottom left is a picture that one Matt Frost from AOM or Google and visit our Hangzhou office. So we have a team in the Silicon Valley and a team in Hangzhou and a team in Beijing. And we hope we can contribute to the deployment, a wider deployment of AV1. That's all we are here about. Thank you so much.
Thank you so much, Zoe, for being here. We want to also see if we can get some questions from the audience. If anybody has any questions, then Preston will be coming around with the microphone. The hands at the front, down here.
In your real-time use case, are you using multiple threads? How many cores are you using?
About 1 core.
Okay, there's a 1 core result.
Yes.
Okay.
The customers give us the feedback. Basically, if they have a 4 core or 8 cores, they don't want us to go over 20% of the usage because they said real time they have a lot of other things they want to worry about.
Yeah. Okay. Thank you.
And then there's a question at the back down there as well.
But it's on PC. It's far away from now. Right now, not far away. So we have to consider it's not in mobile device yet.
Hi, Zoe. That's an amazing presentation. Thank you. The speed improvement over LibAOM that was claimed of 14x, at what point, at which point in AOM's development was that made?
I list down there. I think I gave I think I gave the commit member down there. But I would say that AV1 is going faster. Where is it? I think here. It's February. So, and also it's CPU 0. So I try to avoid talking about the speed comparison for this experiment. It's mainly talking about the bit rate saving about this. Because when you do some other things, further things, you can reduce actually the complexity a lot by comparison against CPU 0. I'm also a supporter to LibOM because it's sitting there, it's open source. Our work borrows a lot of knowledge that has been put in LibOM. So I don't think LibOM CPU 0 has been heavily optimized in terms of encoder, sitting there mainly for the bit rate benchmark.
All right. Any more questions from the audience? One more down the front here. And then I have one from remote as well.
Hi, I was just wondering whether the ML portions are running on the CPU or the GPU.
Oh, it's all on the CPU right now, yes.
Thanks.
So I'm talking about the ML part because we want to keep the simple ML part at this moment. AV1 is already complex encoder. We don't want to get another layer of complexity to that. That's why I say we are customer-driven. So when our customers talking to us, they actually have the 264 or 265 in their mind. So we try to get a better performance, but just want to show that AV1 can be faster. That's the message we want to put out, yes.
Thank you so much. And then another ML question from the remote participants, the hard room of technical people here. So ML has a lot of potential, but getting fast performance remains challenging. Can you comment some on that?
I think when people think about ML, I think they can't get away a lot of time from the use of deep learning. So I think ML still sitting there for a long while when I was, for my graduate, because I'm old, and then we will use some neural network actually doing some lot of recognitions. And so if you just think about, like I just mentioned, 2-layer or 1-layer neural network with only 128 nodes, you will be amazed what kind of result you can get, because it's learning. And you always, when you put some hard code, I think a lot of encoder, including ours, has a lot of hard code parameters. Those are the invaluable, I think those part of code are very valuable or invaluable. I think that's an asset of the encoder, one of the many assets of the encoder. But you can, I would recommend you just search neural network for the LibOM. There's a lot of CLs down there. It's already sitting there. And you can just take a look and then compare the after and before the performance and also the comments to get, then you will get a very detailed idea of how much neural network can get to you. At least that's an example. It doesn't mean you have to rely on that, but that's an example.
Great answer. Thank you so much. Thank you.
Thank you.
Thank you for coming, Zoe. All right.